Hello everyone, welcome to this training session on statistical analysis using Excel. As a part of this session, we'll move slightly from the basic statistical calculation world to a concept called probability. How are these two worlds linked? See, as we have defined in the beginning, the primary purpose of statistics is not just limited to calculations and presentations. I should be able to derive some valid inferences out of the data using statistics. So basically, using the past knowledge, using the historical data, I need to come out with some kind of estimates which can help me to predict the numbers in the future. For example, based on our past observations in this data, we have come out, let's say, with the number of males being something, number of females being something, or probably the marital status being some numbers, the divorce being some numbers, or even on the scale data, the weights more than, let's say, 90 kgs, these many people are there, cholesterol more than 200 units, these many people are there. So some kind of an intelligence based on the patterns in the data we have to develop, so that I can use this kind of an intelligence or a summary that has been developed out of it into a generalized form. Here we have taken a data of 100 people and we have got different numbers associated with different variables, probably 50 males, 50 females. This knowledge, irrespective of the size of the sample and probably for the entire population data, I may have to make some kind of conclusions at that level. So whatever the numbers that are at the small scale, I should have some kind of a mechanism to take it to a large volume of data, and that is where probability is helping out with. All the numbers that we have got in the when we have worked on a sample of data, the probability helps us in translating it into a percentage form or into a relative form, which can give us the values between 0 and 1 itself. It's like saying, okay, what is the proportion of people who do light exercise compared to the total 100 people? Which means, if I assume that this 100 people are completely random in nature, probably it gives me some kind of a starting point. Let's say 15% of my entire population will do some kind of a light exercise. So using the sample, I can actually start off predicting something on a larger scale, and that is where probability will help us out with. Alright, so to start with, it is nothing but it is a percentage form or a relative form of the frequency distribution itself. But how do we use that to do the predictions in future? We'll look at them as we move along. Alright, so let's create some questions based on this. The most commonly used probability based questions, and based on that let's try to sum up our analysis. We'll try to derive some kind of rules and some kind of theorems, and based on which we can apply some of we can compute some of the probabilities based on the data. So to start with, let me create a question using the frequency table for marital status or for smoking status compute the probabilities for each of the statuses. Right, so to start with, we are using only the frequency tables itself. So we have already seen how we compute the frequency table, right? So let me quickly use the pivot table itself to compute the frequency table. So I'll say insert the pivot table, right? Because we have already used it, I will not spend too much of a time in discussing this. So on this pivot table, I am simply computing the different smoking status levels. So I'm dragging this into the row labels, and here I don't want the blank smoking status, so I'm removing out the blank, and probably the smoking status, again I'm dragging it onto the value label. So overall it is giving me the count of 47 people do not smoke, 16 are heavy smokers, and 37 are occasional smokers. So here the thing is very simple. If I have to translate this into probability, it is nothing but it is a relative frequency which I am taking. Probably the same frequencies, if I had expressed in percentage form, we are calling that as the relative frequency or a probability. So it's as good as probably I can use the same table itself, again drag the smoking status, but this time put the count not in a number form. I go to this value field settings, and probably I'll say show it as the percentage of column total. Alright, so it is telling me that 47% or 16% and 37%, and this is what I can associate to. So I can simply say the probability of do not smoke is 47%, the probability of heavy smoker is probably 16%, and the probability of occasional smoker is 37%. What does this mean? Now, if this sample is a very random sample, no biased kind of a sample, what it is saying is there is a 47% chance of finding a person who does not smoke. There is a 16% chance that a particular person whom I have picked up is a heavy smoker, and a 37% chance that he or she is an occasional smoker. So based on the existing data, we are creating some kind of a percentages so that we can very well use it for our futuristic calculations. Let's say if I want to say, a person, he is a smoker, the average life expectancy is 60 years. Occasional smoker will have 65 years, and does not smoke will have 80 years. Now based on that, find out what is the life expectancy of the people. So if this kind of thing has to be found out, I need to know what proportion of the people in the country are smokers, non-smokers, and occasional smokers. So that is where probability will help us out with. On a sample of data, do some kind of calculations in terms of percentages, and probably use that information for the next set of calculations. That is what is one aspect that we can arrive at using the concept of probability. Now, it is just not for a frequency table one dimensional. Probably even a two dimensional frequency table also we can do a similar kind of analysis, like your contingency tables. Using the contingency tables for marital status and smoking status using the contingency tables for marital status and smoking status, compute the probability for each cell. So I can very well create a two-dimensional table also involving two variables, and I can still compute the probabilities, because everything expressed in a percentage form is what we are calling as the probability. Alright, so how do I interpret that? Let me just plot another pivot table there. I can say insert pivot table. This time again between, I'll select this data. Here I require a two-dimensional stuff, right? So I'll pull out the smoking status again here, but the gender I'll pull here, and again either the smoking status or a gender or even an ID, I can pull it onto the value label. Here, because I don't need blanks both in the row as well as in the column, I'll remove the blanks, right? And this is what is the distribution. In the frequency distribution we got something like this, but the same frequency distribution if I allot it in a percentage form. So I'll go to this value field settings, show value as, and I'll say percentage of the total. Alright. So what does this mean to me? There is a 7% chance that a female is a heavy smoker. The person whom I am selecting is a female and also a heavy smoker. Or probably if you try to look at it in a slightly generalized world, if I have to generalize that statement, I can very well make that 7% of the total population are females, heavy smoking females. 9% of the total population are heavy smoking males. Or probably you can talk about 25% of the total population are females who do not smoke. So that kind of categorization you can very well do. If you think that the total population in the country is 100%, 7% is constituted by the females who smoke, 22% is constituted by the males who do not smoke. Like that you can very well break up the data. So just with a small sample set, using the concept of probability, we are able to generalize some of the calculations so that the usage becomes more and more comfortable. So probably here if I have to say, if I have to write it slightly better, we'll write it as probability of does not smoke and female is 25%. Getting it? 25%. Probability of heavy smoking and female is 7%. Like that we will be writing. Probability of occasional smoking and female is 18%. So here also you can write things like probability of does not smoke and male is around 22%. Like this is the probability way of representing the same. Probability of heavy smoking and male. So we are bringing in two variables together in this analysis. So the probability of occasional smoking and male, it is coming out to 19%. So these are the different percentages that are coming out, and whenever I am taking two variables together, I am writing it as an AND relation, especially when I establish with a 2 by 2 contingency table. It is established as AND relationship between the two variables. The probability of choosing a person who is a female and a heavy smoker is 7%, like that. Now, apart from probability, so in this probability, what is that we are talking of? The probability of intersection between the two. This is another term. Technically, when I take two variables together and try to find out their probabilities, we call that as intersection rule. The intersection between the two variables, or probably people call it as joint probability of occurrence of two or more events. So this is what we call, or probably sometimes it's also called as the multiplication rule. All these means one and the same. Now, if I want a scenario where we talk about addition rule, where it is like OR kind of a relationship. Find what, or probably what is the probability that a person selected at random is a male or a heavy smoker. So I'm not talking of AND, I'm talking about a OR. OR means either one of them can be a possibility. So we are talking about a person being either a male or even a heavy smoker. So males, so all these are included as a part of our group, or a heavy smoker. So whosoever is not belonging to the category of male but still is a heavy smoker also is being included in the group. So even this 7% is also included. So that probability will become 57%. So that is where if we are using these kind of logics, if we want A or B, something of one variable or something of another variable. So when these kind of scenarios crop up, we can use the addition rule. So probably in this case, I may have to write it as probability of male or heavy smoker. This kind of things always come out with the formulas like probability of male plus probability of a heavy smoker minus the probability of male and heavy smoker. Now we have all the values. What is the probability of a male? We got that the males are 50%, females are 50%. So the probability of a male is 50% plus probability of heavy smoker. What is the probability of heavy smoker? I can look at here, which is 16%. Irrespective of a male or a female, the heavy smoker probability is 16%. So I'll write it as 16% minus the probability of male and heavy smoker. What is the probability of male and heavy smoker? This is 9%. So I'll write it as this, which is coming out to 0.57, which is what we have also looked at when we have taken the values, this along with this. So whenever we have a requirement of OR in our data, we will go ahead with the addition rule of probability. And now the next thing which we have to be looking at is what we call as conditional probability. conditional probability. Here the scenario is slightly simple. When we talk about the two events, assuming that one of them has already occurred, I want to find out the probability of the second one. For example, I'll write a couple of questions. What is the chance of selecting a heavy smoker given the person is a female? Or probably the same question can be translated slightly better. What proportion of the females are heavy smokers? Or what is the probability of selecting a female who is a heavy smoker? So given that a female is already selected, I want to find out what is the chance that this person smokes heavily. Or probably I can do it the other way also. What is the chance of selecting a female given that the person selected is a heavy smoker? Now, what are the typical scenarios that are being coming out here? We are talking about, out of the two variables which we have used to form our contingency table, the value of one of the variables is known. In the first question, it is known that the person whom I have selected is a female. Or probably in the second case, it is known that the person whom I have selected is a heavy smoker. So, we are talking about selecting a person on the second variable, assuming that in the first variable the value is already known. Right? So those kind of things, we call them as conditional probabilities. So probably how do I represent these conditional probabilities? The probability of selecting a heavy smoker given is like with a vertical line, given female. This is what we are being asked about. What about the next one? Probability of selecting a female given that the person is a heavy smoker. So any English language, if you are able to translate it into a probability language, we are getting these kind of values. Now how much should be the case? If I go back again to my data, given that the person is already a female, so which means my lot is only these many people now, because it is known that the person who is selected is a female. So obviously that person cannot be among this 50. That person will be only among these 50 people. And so out of this 50, what is the chance of selecting a heavy smoker? So there are 7 in this group out of this 50 who are heavy smokers. So what is this? This goes with 7 by 50, wherein you are coming out with, there is a 14% chance that if the person selected is a female, that person may be a heavy smoker. There is a 14% chance of selecting a heavy smoker if it is known that the person selected is a female. Now try to do the same logic. Given that the person is already a heavy smoker, So only 16 people. So that selected person could be only from this lot of 16. Right? That person can be only from this lot of 16. We are saying what is the chance of selecting a female. Out of the 16, 7 of them are female. So when I translate that into a probability language, this comes out as 7 divided by 16. So this works out to around 43.75. If it is known that the person is a female, is a heavy smoker, so probably the other way of writing this statement is 43.75% of the heavy smokers are females. Because it's already, the group is given. Or probably how do I write this statement? 14% of the females are heavy smokers. This is how we can typically use knowledge to translate it into some meaningful statements. So whenever I am talking about only within one group the presence of the other variable, not in the entire data, but only in one subgroup, if I want to understand the other variable, we will use the concept of conditional probability. Right? So in a simple sense, how do I write the formula for this? P of H given F is nothing but P of H and F, probability of heavy smoker and female, divided by the probability of females itself. Probability of females is nothing but only females. Only females is this 50%. The grand totals is what we'll take for only female, only male, or even only doesn't smoke, only smokes, occasionally smokes kind of stuff. So these grand totals, both of the row and the column here, are also called as marginal probabilities. Marginal probabilities are the grand totals, or which are also called as unconditional probabilities. So basically it is like, what is the probability of a person being a female? 50%. Probability of person being a heavy smoker? 16%. I am not sure about the gender associated with that person. But out of the total population, 16% of them are heavy smokers. Or 47% of them do not smoke at all. So that is what we are calling as unconditional or marginal kind of a probability. And we are also talking in terms of conditional kind of a probability. Here comes another important aspect for us. A few more relationships. If I get probability of let's say H and F, if it comes out as probability of H and F, if it comes out as probability of H multiplied by probability of F, which means if this kind of a relationship in between any two variables, their intersection is same as the multiplication of their independent marginal probabilities, we call those two kind of events as completely independent events. So we have seen here what is the probability of H and F. Probability of H and F here is 7%. I'll try finding out probability of H multiplied by probability of F. What is the probability of H here? We have got the marginal probabilities above. The probability of H is 16%, probability of F is 50%. Okay, so 16% into 50%. It has come out to 0.08%. Whereas when we are looking at the intersection H and F, we got it as 7%. So in this case, we cannot say that the events, that the two variables gender and the smoking status are independent. We cannot say that the gender and smoking status are independent, because probability of H and F has not come out as probability of H multiplied by probability of F. So wherever such kind of relationship comes out, we call them as independent events. Otherwise also you can see, how do I find out if they are not independent? The simple way of finding out probability of H and F is, if it comes out like this, probability of H multiplied by probability of F given H. This is the typical way to arrive at that. Now we know that the probability of H is 0.16 multiplied by probability of F given H is this much. So which has worked out to 0.07, which is the same as probability of H and F. So in general, we see this kind of a relationship exists between probability, because we know that the probability of H given F given H is nothing but probability of F and H divided by the probability of H. So do a cross multiplication, you will get probability of F and H is nothing but probability of H into probability of F given H. But if it so comes out that it is the multiplication of their independent probabilities or marginal probabilities, we associate that to be independent kind of events. So this is one more thing we have to be comfortable with when we are trying to resolve some kind of conclusions from the data, right? All these calculations to start with, they are applicable on your nominal or ordinal categorical kind of a data, right? So all these basic rules of probability, whether it is the multiplication, which is AND kind of rules, or addition, which is OR kind of rules, all these are primarily applicable on nominal or ordinal categorical form of data. So conditional probability is one more aspect which we need to be comfortable with, right? So from the data, these are the various aspects in terms of computation. These are the various aspects that we need to be comfortable with. At least the topics wise, we should be comfortable with the usage of conditional probability, the marginal probability. How do I link the contingency tables to the probabilities? How do I use the frequency distribution to probabilities? And how do I test for the independence between the two variables? These are some of the things that we have to do. And sometimes what happens is, there are a couple of more things we should be comfortable with. Let's say I'll deal with another element called total probability. There is another concept which I would like to bring up here. Total probability rule. What this rule is helpful for us is, if at all I am able to identify mutually exclusive and exhaustive set of events. What are they? Mutually exclusive is if one of them occurs, the other does not occur. Probably, if I am talking about the probability of male in the data, probability of selecting a male, it is 0.5, and probability of selecting a female also is 0.5, or for that matter any other variables also. Here, if I select a male, I cannot select a female. If I select a female, that person cannot be a male. So they are mutually exclusive kind of variables. That particular variable which has only one value to any record, right? If I am talking about the marital status, there can be only one to a selected person. Or even if I am talking about the education qualification, there can be only one to any selected person. But if I am talking about the list of education qualifications, where multiple qualifications also can be listed for a single person, then we don't say that they are mutually exclusive kind of events. So at least in this example, male and female, the gender, because any person at a time can have can associate any person can be associated only with one value, we call them to be mutually exclusive kind of events. So once I have a mutually exclusive, and what are exhaustive? There cannot be any other value apart from male and female in that data, right? Or in simple sense, if I take the sum of all their probabilities, it should be equal to 1. So in case I come across any such kind of events where they are mutually exclusive, if one occurs, the other, no two values can come out simultaneously for a single record, and they are exhaustive. No other value also can come out for that record apart from these values. Those set of events, no two values can be associated to a same record, and no other value apart from whatever are listed can be associated with that record. Those kind of events are called as mutually exclusive and exhaustive events. If at all I have such kind of events, what it is said is, I can try to find out the probability of any other event. Let's say the probability of heavy smoker. Let's assume that from this data I have no idea of what is the probability of the smokers, heavy smokers. What it says is, I can find out the probability of any of these things through a simple logic. What it says is, you take this H with respect to each of these mutually exclusive events. So it's like the probability, if you know at least these things, probability of H given males multiplied by the probability of male. What does this mean? I'll discuss about it. Probability of H given female multiplied by the probability of female. Even using this, you should be able to find out the probability, unconditional probability of a person being a heavy smoker. What is this telling us? Associate any new event to the set of mutually exclusive and exhaustive events. If you know at least, see, overall you may not know what is the proportion of heavy smokers, but at least even if you know that some 20% of the males are heavy smokers and 10% of the females are heavy smokers. At least if that kind of an information if you have, you can very well find out what is the proportion of the heavy smokers overall, provided you know even the unconditional probabilities of male and female. That is what is the total probability rule talking of. In simplistic sense, for any event, if you know if you know the set of mutually exclusive and exhaustive events, the values which are mutually exclusive as well as exhaustive, any other probability, any other unconditional probability can very well be found out using this total probability rule. Each of the element, each of map the unconditional event with as a conditional to each of the mutually exclusive and exhaustive outcomes and add up the probabilities. That is what will result in the total unconditional probability of an event. So here if we know the probability of males is 0.5 multiplied by probability of H given male. Okay, probability of H given a male. Out of the males, 9 of them out of 50 are smokers, which is 0.18, 18% of the males are smokers, plus probability of H given F, we have already found out 0.14 multiplied by probability of F, which is again 50%. So all I can simply say is 16% of my overall population are heavy smokers. So in this case, at least we have the value, so we don't need to bother. But this relationship actually helps us out at a later point very well. And based on this concept itself is what we have, what we call as the Bayes theorem. What it says is, let's say I want to find out the probability of F given H. What it says is, if I have these probabilities, probability of F by probability of H into probability of H given F, the reciprocal of it if I know, I should be able to find out the probability of F given H. So let's say we already know probability of F given H because from the data we were able to find it out. But in some cases, if I can't have the access to the raw data and if I only have the probabilities, which are the summarized values only I have, here we are deriving the probabilities from the raw data. But sometimes what happens is, we will not have the raw data. Some kind of a published summary is what will be available to us. So based on this, we may have to calculate the other kind of probabilities, and that is what will help us out in doing this here. Okay, so probability of F, we know that the probability of a female is 50%. Divided by probability of H, we have found out just above using the total probability rule. I'll take it as 0.16. Multiplied by probability of H given F, let's assume that it is known. I'll do it as 0.14, which will work out to 0.4375, and which is what was equivalent to the value which we have computed probability of F given H. So these are some of the, you have to, when you are working on the raw data, please remember these things as the relationship between the various sets of variables, because when you have a raw data with you, all these will look like pretty silly to operate. But in most of the cases, see, you will have just a summary saying 14% of the males or 18% of the females are smokers, or 25% of the males do not smoke. Like this, if you get some kind of summaries, and probably you may have to build the reciprocals. Let's say now given a person is a heavy smoker, what proportion of the smokers are females. You know what proportion of the females are smokers, but you want to find out what proportion of the smokers are females. So for these kind of stuff, the Bayes theorem along with the total probability rule will definitely help us out. If we have the raw data, all these will look more and more redundant. But if we are operating in a scenario where we only have summaries of values, that is where the testing for independence, the checkout for the conditional probabilities, the total probabilities, the Bayes theorem, all these concepts will play quite an important role, right? So to get into the practical usage or slowly getting into the world of predicting and forecasting, it is very much essential that we understand the concept of probability, because slowly what we will observe is this probabilities itself will get translated into the probability distributions, which means at various levels what are the probabilities. Instead of only for one value, we will look at the probabilities for series of values, create that as a distribution and use that distributions for our estimations and prediction processes. So understanding the basic concept of probability is definitely required even from statistical estimations standpoint. All right. I hope this session has given you a decent level of insight into the world of probability, and especially the aspects like the basic definition of the probability, how do you compute the probability from the raw data, and also from frequency distribution as well as two-dimensional contingency tables. How do I use the conditional probability from the data? How do I use marginal probability computation? How do I use the multiplication and the addition rules of probability as well as the total probability rule? And finally, how do I use the Bayes theorem to find out the upgraded probability of an event subjected to the occurrence of some other event? So if you have any more further queries regarding this, feel free to get in touch with me. I would be very much happy to clear your doubts. So you can even give me a call on the number that I have provided below, or you can send in an email to me at the email address vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.